You are walking along a dry riverbed, roughly 11,000 years ago, somewhere in the hill country of what is now northern Iraq. Something catches your eye in the gravel. A stone unlike any other stone you have ever picked up. It is heavy for its size, heavier than it has any right to be. It has a strange reddish-orange color you have never seen in ordinary rock. And when you strike it against another stone, the way you would strike flint to shape a tool, it does not chip. It does not shatter. It simply bends, dents, and holds a new shape, the way wet clay does. Except this material is cold and solid, and clearly not clay at all. Every material you have ever worked with your entire life has behaved according to one simple rule, learned so early and so consistently that you have never once had reason to question it. Rocks break. This one does not. And the moment you realize that you are holding the beginning of an entirely new category of human technology, one your species had never encountered before and would spend the next 10,000 years learning to master. So, how did humans discover copper? The answer starts with an extraordinary geological accident that a small number of places on Earth contain a metal in a form humans could use straight out of the ground with no chemistry at all, and it ends, eventually, in the wiring running through the walls of the room you are sitting in right now. Let's start with why copper was even possible to discover this way in the first place, because almost every other metal humans use today simply is not. Iron, aluminum, tin, zinc, all of these exist in nature locked inside chemical compounds called ores, bonded tightly to oxygen or sulfur, and extracting the pure metal requires real chemistry, specifically smelting, applying intense heat in the presence of carbon to break those chemical bonds apart. You cannot stumble across a lump of pure metallic iron lying on the ground. Copper is one of the very small handful of metals that occasionally breaks that rule. In a limited number of geological locations around the world, copper exists in nature as native copper, meaning pure, metallic, elemental copper, sometimes in nugget form, sometimes as branching, root-like veins running through rock, requiring no chemical transformation whatsoever to use. You can pick it straight out of the ground and start shaping it. Nature, in a small number of very specific places, had already done the hardest part of metallurgy before any human ever showed up. The oldest known worked copper object anywhere in the world reflects exactly that. A small copper pendant was recovered from Shanidar Cave in northern Iraq, a site that has produced evidence of human occupation stretching back tens of thousands of years, and this particular object has been dated to roughly 8,700 BCE, close to 10,700 years old. Chemical analysis indicates it was made from native copper, cold hammered into shape without any heating or chemical processing at all. Nobody smelted anything to make it. Someone simply found a strange, heavy, bendable stone, realized it could be worked with hand tools the way no ordinary rock could, and shaped it into an ornament, small enough to wear, valuable enough, apparently, to be kept and eventually lost or deliberately placed where archaeologists would find it thousands of years later. That single small pendant represents, as far as the archaeological record currently shows, the very beginning of human metalworking. Similar early copper use shows up at other sites across the same broad region in the millennia that followed. At Kayonu Tepesi in southeastern Turkey, archaeologists have recovered small cold-worked copper items, pins, beads, hooks, dating to roughly the 9th and 8th millennia BCE, and at the famous Neolithic settlement of Catalhouk, also in Turkey, copper beads appear in burials dating to around 7,000 BC. In every one of these early cases, the copper was cold-worked, meaning simply hammered into shape at room temperature, exactly the way our imagined riverbed discoverer might have done it, using nothing more sophisticated than a hard stone as a hammer. Nobody was melting copper yet. Nobody understood it as a substance that could be poured into a mold. It was, for these first few thousand years of human metalworking, treated essentially as an unusually cooperative kind of stone. But cold-working copper by hand runs into a real physical problem, one that any early smith would have discovered the hard way through frustrating trial and error. Hammer a piece of copper repeatedly, and it does not simply get thinner and more refined the way you might expect. It gets harder and more brittle, a phenomenon materials scientists today call work hardening. The repeated mechanical stress rearranges the metal's internal crystal structure in a way that makes it increasingly resistant to further shaping, and eventually, if you keep hammering, the metal will crack and shatter, the exact failure early metalworkers were trying to avoid by choosing copper over stone in the first place. The fix, eventually discovered, is annealing, heating the copper to a moderate temperature, and then letting it cool, which resets that internal crystal structure and restores the metal's softness and flexibility. Nobody understood the underlying physics of what they were doing, but somewhere in the millennia after that first Chanadar pendant, early smiths worked out, purely through observation and repetition, that periodically warming a piece of copper in a fire during the hammering process let them shape it further without it cracking. It was empirical materials science, discovered centuries before anyone had a word for either metallurgy or crystal structure, passed down not through any written formula, but through a craftsperson simply remembering and teaching an apprentice that the metal behaved better after a visit to the fire. Now here is where the story of copper takes a genuinely remarkable turn, because the discovery of native copperworking did not happen only once, in only one place. It happened again, completely independently, on the other side of the planet, in a location so rich in pure metallic copper that it produced one of the strangest and most underappreciated chapters in the entire history of ancient technology. Around the Great Lakes region of North America, particularly near Lake Superior and Isle Royale, geological forces created one of the largest and purest concentrations of native copper anywhere on Earth. Copper so pure and so abundant that entire boulders of it could be found lying exposed at the surface. Indigenous peoples in this region, part of what archaeologists now call the Old Copper Complex, began working this material with cold hammering and annealing techniques that closely parallel what was happening independently in the ancient Near East, producing spear points, knives, awls, and ornaments. Radiocarbon dating places some of the earliest activity at sites associated with this tradition several thousand years into the past, with dates for the peak of the complex generally falling somewhere in the range of roughly 5,000 to 7,000 years ago, and some researchers have argued for even earlier activity at certain sites. There is no plausible route by which this knowledge could have traveled from the Near East to the Great Lakes region at that period in history. The two traditions arose from the same underlying reality: humans encountering pure, workable metal lying exposed in the landscape, and independently arriving at the same basic technique of cold hammering and periodic heating to shape it. What makes the Old Copper Complex especially fascinating is what it never became. Despite thousands of years of sustained copper working, involving genuinely sophisticated cold working techniques, this tradition never developed smelting. It never needed to. The Great Lakes region had so much accessible native copper that there was no practical pressure pushing anyone toward the much harder chemical problem of extracting metal from ore. Necessity, in this particular case, simply never arrived to drive further innovation. Objects made from Lake Superior copper have been recovered from archaeological sites remarkably far from the source material itself, in some cases hundreds of kilometers away, evidence that a genuine trade network moved worked copper items across a substantial portion of the North American continent, long before European contact and, in some cases, thousands of years before anyone in the Old World had figured out how to smelt the metal at all. That detail matters because it shows the Old Copper Complex was never a marginal, isolated curiosity. It supported real economic exchange, moving finished tools and ornaments between communities that may never have directly visited the source deposits themselves, an entire regional economy quietly built around a metal that most conventional histories of technology, written from a European vantage point, tend to overlook almost entirely. Back in the Old World, necessity did eventually arrive, because native copper, while genuinely useful, is relatively rare and geographically limited. If you wanted more copper than nature happened to leave lying around in a form you could pick up and hammer, you needed a way to get it out of ordinary-looking rock, and that meant solving an entirely different, much harder problem: chemistry. The earliest solid evidence for true copper smelting, meaning the deliberate chemical extraction of metal from, or using heat, comes from the Balkans, from sites associated with the Vinca culture in what is now Serbia. At a site called Belovod, archaeologists led by Miljana Radivojevic uncovered evidence of copper smelting activity that chemical and radiocarbon analysis dated to roughly 5000 BCE, publishing their findings in the Journal of Archaeological Science in 2010, findings that pushed the known origins of copper smelting back significantly earlier than most historians had previously assumed. A related site, Plotnik, also in Serbia, has produced evidence of copper tools, including axes, produced through smelting on a scale that suggests genuinely organized, specialized metallurgical activity rather than isolated, one-off experimentation, making the Vinca culture's copperworking tradition one of the earliest known organized metallurgical industries anywhere in the world. So, how did anyone figure out smelting in the first place? A process that requires heating specific, colorful minerals to precise temperatures in the presence of charcoal to trigger a chemical reaction nobody at the time had any theoretical understanding of. The leading hypothesis among archaeologists connects the discovery directly to pottery. Malachite, a vivid green mineral that is chemically a copper carbonate, and azurite, a related deep blue copper mineral, were already being used by Neolithic communities as decorative pigments and glazes on pottery, well, before anyone was deliberately smelting metal. Pottery kilns of this period were capable of reaching temperatures in the range of 800 to 1,000 degrees Celsius, hot enough, in the presence of the wood charcoal commonly used as fuel, to trigger exactly the chemical reaction, called carbothermal reduction, that strips oxygen away from copper minerals and leaves behind small beads of pure metallic copper. Under that theory, someone decorating pottery with colorful malachite, or simply firing pots in a kiln built near copper-rich rock, would have occasionally noticed small, unexpected, shiny metallic beads forming where the green mineral had been, an accidental byproduct of an entirely different craft. Repeated often enough, by enough different potters across enough different kilns, that accident eventually became recognizable, then intentional, then a deliberate, controllable technology in its own right. It is worth pausing on how strange that sequence actually is. The single most consequential chemical discovery in the entire history of metallurgy may not have come from anyone trying to solve a metallurgical problem at all. It likely came from someone trying to make a nicer-looking pot. Once smelting was understood, even imperfectly, it changed the scale of what copper metallurgy could accomplish, because it decoupled copper production from the accident of geography that had limited native copper use to only a handful of regions on Earth. Copper ore, unlike native copper metal, is relatively widespread. Smelting technology spread outward from its early centers across the eastern Mediterranean and the Near East over the following centuries, reaching Egypt, where pharaonic expeditions organized mining operations at sites like Serabit el-Khadim in the Sinai Peninsula, extracting both copper and turquoise under harsh desert conditions using conscripted and enslaved labor. Inscriptions at the site recording the presence of these mining expeditions across multiple dynasties. And copper spread as a trade good, not just a technology, produced one of archaeology's most vivid pieces of physical evidence for how interconnected the ancient world already was, thousands of years before anyone would call it globalization. In 1991, hikers in the Ötztal Alps on the border of Austria and Italy discovered the naturally mummified remains of a man who had died roughly 5,300 years ago, now known as Ötzi the Iceman. Among his equipment was a copper axe, and later chemical and isotopic analysis of the metal traced its origin to ore deposits in southern Tuscany, in what is now Italy, hundreds of kilometers from where his body was ultimately found. A man carrying a tool made from metal mined and smelted a significant distance from where he lived and traveled is direct, physical proof that copper and the raw materials, or finished goods made from it, were already moving through organized trade networks well before written history in the region even begins. It is a small, almost domestic detail, a single traveler's axe, and yet it does more to establish the reality of prehistoric long-distance trade than pages of theoretical argument ever could. No location illustrates copper's importance to ancient trade more directly than the island that eventually gave the metal its name. The eastern Mediterranean island of Cyprus contained rich copper deposits, and by the Bronze Age, Cypriot copper was being mined, smelted, and exported across the entire Mediterranean world in enormous quantities, making the island one of the most important metal-producing centers of the ancient world for well over 1,000 years. Its copper turning up in shipwreck cargoes, in temple dedications, and in diplomatic correspondence between kings who never met each other, but who clearly understood exactly how much a shipment of Cypriot ingots was worth. The Romans referred to the metal as AS Cyprium, literally metal of Cyprus, a phrase that gradually simplified over centuries of use into cuprum, which is the direct root of the modern English word copper, and of the element's chemical symbol Cu, an entire chemical element still used in every electrical wire and every plumbing pipe on Earth today, carries a name that is, at its core, simply the name of a Mediterranean island that happened to produce an extraordinary amount of it 4,000 years ago. Copper on its own, however, has a real limitation as a tool-making metal. It is relatively soft compared to what would eventually replace it, prone to bending or dulling under exactly the kind of hard, repeated impact a weapon or a heavy-duty axe would face. Sometime in the centuries surrounding the 4th millennium BCE, metalworkers in the region around Anatolia and the Caucasus discovered, likely through experimentation with or sources that naturally contained trace amounts of arsenic, that mixing copper with a small percentage of that element produced a harder, more durable alloy, arsenical copper, capable of holding a sharper edge and bending less easily than pure copper alone. That discovery represents the first real step away from pure copper metallurgy and toward what would eventually become the Bronze Age proper. Once metalworkers later learned that tin produced similar and ultimately more reliable and less toxic hardening effects. But that transition, the specific shift from copper to bronze, is really the beginning of an entirely separate chapter in metallurgical history. The point that matters here is that every one of those later innovations, arsenical copper, true tin bronze, and eventually iron and steel, was built directly on top of a foundational skill set, controlling fire, recognizing or understanding how metal behaves when heated and cooled, that human societies had spent thousands of years developing specifically around copper and copper alone, long before anyone had reason to experiment with mixing it with anything else. And just as with the old copper complex in North America, copper metallurgy did not spread outward from a single old world point of origin to cover the entire globe. It arose independently more than once, wherever the right combination of accessible ore, fuel, and technological curiosity happened to line up, a pattern that shows up again and again across the history of ancient technology. In China, archaeological evidence points to independently developed bronze metallurgy emerging by at least the early 2nd millennium BCE, associated with the Iraqi culture, a tradition that developed distinctive casting techniques, particularly the use of complex, multi-part ceramic piece molds, quite different from the hammering and simple mold casting methods that dominated early metallurgy in the Near East, and one that would go on to produce some of the most technically sophisticated bronze ritual vessels anywhere in the ancient world. In the Andes, in what is now Peru and Bolivia, pre-Columbian metalworkers developed their own sophisticated copper-based metallurgical tradition entirely independently of any old world contact, including distinctive techniques for creating tumbega, a copper-gold alloy prized for its color and workability, alongside genuinely inventive surface treatment methods that could make a copper-heavy alloy appear almost entirely golden through selective chemical removal of the copper from the object's outer surface, a technique so effective that Spanish conquistadors, arriving many centuries later, were frequently and famously fooled into believing they had found solid gold. None of these traditions, the Balkans, the Great Lakes, China, the Andes, borrowed the underlying idea from each other. Each one arrived independently at the recognition that this particular reddish metal, whether found native or coaxed chemically out of colorful stone, was worth the enormous effort required to work it. The story of copper does not end in antiquity, and in some ways its single most consequential chapter came thousands of years after the last Bronze Age sword was forged. Once humans discovered an entirely new property of the metal that had nothing to do with hardness or edge retention at all. Copper conducts electricity exceptionally well, better than almost any other practical, affordable metal available in large quantities. That property meant almost nothing to anyone before the 19th century, because there was no practical use for controlled electrical current at any meaningful scale. That changed dramatically following the work of researchers like the English scientist Michael Faraday, whose experiments on electromagnetic induction in the early 1830s laid the essential groundwork for generating electrical current using motion and magnetism, work that, at the time, struck most observers as an interesting scientific curiosity rather than the foundation of an entirely new global industry. As the technologies built on that discovery, the telegraph, the telephone, and eventually large-scale electrical power distribution, developed rapidly through the remainder of the 19th century, copper's ancient, purely mechanical usefulness as a soft, workable metal for tools and ornaments was suddenly overshadowed by an entirely different property that nobody working a copper axe at Plocknick or a copper pendant at Shanidar Cave could possibly have anticipated. Today, the overwhelming majority of copper mined anywhere on Earth goes not into weapons or jewelry at all, but into electrical wiring, motors, and the vast infrastructure of generators, transformers, and cables that keep modern electrical grids running, a use so fundamental to contemporary life that global copper demand is now treated by economists and industrial planners alike as one of the more reliable leading indicators of the health of the entire world economy, tracked as closely by financial analysts as it once was by ancient traders loading ingots onto ships bound out of Cyprus. So here's the full arc. Roughly 10,700 years ago, someone in what is now northern Iraq found a strange, heavy stone that bent instead of breaking and cold-hammered it into a small pendant, the oldest known worked copper object in the archaeological record. Over the following millennia, similar cold-working traditions using native copper appeared at sites like Keona Tepesi and Catalhook in Turkey, with early smiths gradually, painfully, working out through trial and error that periodically heating the metal during hammering, annealing, kept it from cracking under repeated stress. On the opposite side of the planet, with no possible contact or shared knowledge, indigenous peoples of the North American Great Lakes region independently discovered and mastered the exact same basic technique, working the extraordinarily pure native copper deposits around Lake Superior for thousands of years, producing sophisticated tools without ever needing to develop smelting at all, because the raw material was simply too abundant to require it. Around 5000 BCE in the Balkans, communities of the Vinca culture crossed a much harder technological threshold, learning to smelt metallic copper directly out of colorful or minerals, very likely as an accidental byproduct of firing decorated pottery in kilns hot enough to trigger the necessary chemistry, without anyone understanding why it worked. That knowledge spread across the ancient Near East and the Mediterranean, reaching Egyptian mining expeditions in the Sinai, traveling in the form of a mummified traveler's axe across the Alps, and eventually making the island of Cyprus so central to ancient copper production that the metal and the chemical element itself still carries the island's name today, thousands of years later, on every periodic table printed anywhere in the world. Copper's own limitations as a relatively soft metal eventually pushed metalworkers toward alloying it with arsenic and then tin, launching the Bronze Age and eventually everything that followed it. And completely independently of any of this, entirely separate metallurgical traditions arose in China and in the Andes, each one arriving at sophisticated copper-based technology through its own path, with its own techniques, arrived at without a single shared idea passing between any of these regions. Finally, thousands of years after the last ancient smith set down his hammer, an entirely new and completely unanticipated property of the same metal, its ability to conduct electricity, quietly became the reason copper remains one of the most economically important materials on the planet today. Was the discovery of workable copper a single invention that spread outward from one origin point? Almost certainly not, at least not in its earliest native metal form. The evidence is about as clear as archaeology ever provides on this question. Native copper working developed independently in the Near East and in North America, separated by an ocean, thousands of kilometers, and, in some estimates, very little overlap in time at all. The probability that either tradition learned the technique from the other is effectively zero, close to no realistic chance whatsoever, given the total absence of any plausible route of contact between the two regions at that period. Smelting itself is a somewhat different case, since the archaeological evidence for its earliest development points more specifically toward the Balkans as an origin point before the technique spread through established trade networks across the Near East and Mediterranean, making single-origin diffusion, at something above 60% probability, the more likely explanation for that particular chemical leap, even as entirely separate smelting and alloying traditions later arose, independently in East Asia and in the Americas. Native copper working was less a single invention than an inevitability, waiting patiently in the ground in a small handful of places on Earth for any sufficiently curious person to pick up the wrong-looking stone and notice that, unlike every other rock they had ever touched, it refused to break. Tonight, somewhere behind the wall beside you, there is very likely a length of copper wire carrying the exact electrical current that is powering the device you are using to watch this right now, made from a metal whose very name traces back to a Mediterranean island, whose earliest known use traces back to a small pendant in an Iraqi cave nearly 11,000 years old, and whose independent rediscovery on the shores of a great lake half a world away produced tools that owe absolutely nothing to that Iraqi cave at all. You will not think about any of that when you flip a light switch. You will simply expect the light to come on. And it will, because somewhere in the deep, largely unwritten prehistory of our species, more than once, in more than one place, entirely by accident, a human being picked up a strange stone that would not shatter, turned it over in their hands, felt it give slightly under pressure the way nothing else in their world ever had, and decided to see what it could become instead.